Alright guys, today we're going to be covering domain, which is probably going to be the most important topic in your pre-calc career, aside with our next topic, which is going to be range. But we'll leave that for the next video. Anyway, what is domain? Domain is effectively all of the numbers that you are allowed to plug into your function. It's all the x values that you can plug into your function and not get an error. Okay? So let's start with a fairly simple function. F of x equals e to the x. Okay? The easiest way to start interpreting domain is to think of what the function might look like, which is why it's so important to be able to memorize the general shape of your functions. Okay? Now you can see here that e to the x extends to infinity all the way to the left and to infinity all the way to the right. Even though it keeps getting steeper and steeper, it still goes up to infinity on the right. Okay? And you'll see here that we can raise e to any number. We can raise it to negative 40. We can raise it to like a gazillion, and no problems are going to happen. That's still going to result in a number that exists. Okay? So by that definition, we are able to plug every number in the entire world into this function, and it's going to be all right. It's not going to give us any problems. So if we want to write the domain for that, it's going to be negative infinity to positive infinity. We can put these numbers into our function, and nothing will happen. No problems will arise. Okay? So it's important to note what is happening when we write these parentheses, because there's two types. You can have the soft parenthesis or you can have the hard bracket. So let's first discuss what they mean. If my domain was written as hard bracket 4 with a 5 and a soft bracket, what this means is my domain is including 4 but not including 5. Okay, the way you read this domain is my domain is from 4 inclusive all the way up until 5 exclusive, which means 4 is part of my domain. I can do f of 4 and that's going to be alright. That's not going to give me any problems. I can do f of 4.1. That's going to be fine. But if I do f of 5, that's going to give me problems because 5 is not included in my domain. It's everything up until 5. That's what the soft parenthesis denotes. Now let's move on from there and start considering some of the examples where we might not have a domain of negative infinity to positive infinity. First example is going to be the y equals log x, or any logarithm for that matter. Let's first look at it by drawing the graph. Okay, if I draw the graph of y equals log x, it's going to look a little something like this. Okay, you'll notice the graph does not exist on the left side of my function. And basically what the domain is it's asking the question, where does the line of my graph exist? So if we look at the function, we can interpret why that is. I can never put a negative number into my logarithm, because that's basically telling me what power do I need to raise 10 to in order to get negative 1. I can never raise 10 to any power and get a negative number. Okay? Wherever x is less than or equal to 0. Well, why do we include this equal to? Because if I try to analyze log of 0, and that's asking me what power do I need to raise 10 to get 0. There does not exist such a power. So therefore, the domain of any logarithmic function is if we take whatever's in our parentheses and we set that greater than 0. Those are all the numbers that we are able to put in for x. Okay? If it's not greater than 0, we're going to have a problem. So in this case, we are looking at the domain 0 exclusive all the way up until infinity. Means our domain is 0 to infinity, but not including 0. We can't plug in 0. Let's work through a slightly more difficult problem now. If I gave you f of x equals log of negative x squared plus 2. Okay? In order to find the domain of this, I would need to find where negative x squared plus 2 is greater than 0, or when negative x squared is greater than negative 2. Or if I multiply both sides by the negative, I'll have to flip my inequality when x squared is less than 2. Those are the only points where my function will be defined. So I need to find the x values that correspond to that range, or excuse me, I need to find the x values that correspond to that domain. So if I take the radical of both sides, I'm going to get x must be less than the plus or minus radical of 2. Okay? Remember that negative 2 squared equals 2 squared equals 4. So we need our plus or minus whenever we take a radical, which can be therefore rewritten as x must be less than rad 2, or x must be greater than negative rad 2 for the negative rule we just discussed right here. So to write the domain of this function, the domain would be negative rad 2 exclusive all the way up until positive rad 2 exclusive. Next, we're going to explore the other type of functions. Let's say f of x equals rad x. Let's draw a function of that. That looks approximately like this, okay? Where you can see here that we are not defined on this part of the coordinate plane. So we know that x must be greater than 0. However, if I put x equals 0 into my radical, rad 0 equals 0. So therefore 0 is indeed part of my domain, and this is actually x is greater than or equal to 0. So if I were to write the domain right here, it would be inclusive 0 all the way up until infinity. And we always write infinity or negative infinity with a soft bracket. So now let's try a little bit of a harder example. Let me give you f of x equals rad x minus 4. I need to find whenever this thing, the thing inside my radical, is greater than or equal to 0. Okay? Or when x is greater than or equal to 4. That's where I have my answer. I'm going to write that out in my domain form. So my domain is x can equal 4, and it can be anything greater than it, like this. Now finally, we're going to look at fractional functions or rational functions. F of x equals 1 over x. Let's draw the graph of that. Here you'll notice that we have a vertical asymptote at x equals 0. Okay? So this vertical asymptote tells us that we cannot have x equals 0. That is not allowed because we cannot divide by 0. So if I were to write the domain for this, it would be all real numbers except for 0. So negative infinity up until 0, excluding 0, union 0, not including up until infinity. So let's try an example of this. F of x equals 1 over x squared minus 4. Okay? Whenever I see anything that can be factored, it therefore must be factored. F of x is equal to 1 over x minus 2 times x plus 2. Now, if you're shaky on factoring, or if you've never heard of factoring, please go watch our factoring video. It's very helpful, and it's something you're going to need for your entire pre-calc career. Okay? Therefore, I need to figure out what makes this expression equal to 0. So either x minus 2 can equal 0, or x plus 2 can equal 0. So we need to find when both of those instances are true. The first one is true when x equals 2. The second one is true when x equals negative 2. Therefore, if I'm going to write my domain, it's going to be negative infinity up to but not including negative 2, union negative 2 up to but not including 2, union 2 up to and infinity. That's going to be my final answer for the domain of this function. Now let's try one more example, everyone's favorite, rational functions. I'm going to give you 3x squared plus 9x minus 12 all over x squared plus x minus 2, all minus 4. Okay, let's find the domain of this guy. Like I said before, we always got to factor. So I encourage you to try and factor this on your own and then come back. So what we're going to get after that is we're going to get 3 times x plus 4 times x minus 1 all over x plus 2 times x minus 1, all minus 4. And we're going to pause and we're going to see here that we have a removable discontinuity. Okay, removable discontinuity being a hole in our graph, meaning it is not defined for specifically that x value. So we need to consider when this, our removable discontinuity, is equal to 0. X minus 1 equals 0 occurs when x equals 1. So that's one x value that is not going to be part of our domain. Now we're going to consider the rest of our denominator. We're going to consider when this could possibly be 0. When x plus 2 is 0 occurs when x equals negative 2. So these are the two numbers not going to be part of our domain. And we're going to write our complete domain now as negative infinity up to negative 2 exclusive, union negative 2 up to 1 exclusive, then 1 up to positive infinity. Okay, so you can see here that we have a removable discontinuity as we defined here, and we have a vertical asymptote, which is a discontinuity that was not removable. And so this is how you find your discontinuities, by determining your domain. Alright, thank you guys for watching, and as always, enjoy life.